اوكي بسم الله الرحمن الرحيم. طبعا الليله ان شاء الله عندنا المهندس محمد المطوع، سيرتيفايد اسبن بلس وسيرتيفايد هاي سيس. بياخذكم في رحله مع الاسبن وبيشرح لكم البيسكس وبيمر على المساله اللي المفروض ان شاء الله تسلموها. اذا عندكم اي استفسار ان شاء الله يعني محمد راح يجاوبكم عليه، و I will just leave the floor for محمد. It's all yours وبالتوفيق جميعا.
يعطيك العافيه دكتور، جزاك الله خير. السلام عليكم، كيف الحال شباب؟ مبارك عليكم الشهر الكريم، والله يجعلنا وياكم من صوام وقوام ان شاء الله. So I'd like just to introduce myself. Muhammed Almutawaa. I'm a proud ex-KFUPMer. I graduated with chemical engineering degree in 2017 and my master in petrochemical in 2022. I currently work in SABIC as a process engineer. I have around 5 years of industrial experience in process simulation. And I'll be glad to share the humble knowledge that I have with you, and inshallah we will have a very fruitful session together. I see we have a good number, so without further ado, let us get started. First of all, I would appreciate if the session is more of an interactive session rather than just me talking. So if you have any question, I'll be also asking questions. So let us have back and forth interactions to make the most out of it, inshallah. So first of all, let me ask you why we need process simulation and as chemical engineers. Why process simulation is important to us, if I may ask the question. Yes, go ahead.
Saves time and effort.
Excellent, yes. Basically, process simulation is a tool. You learned all the basics that you come across at college, from mass and energy balance, unit operation, reaction, design, cost, safety, engineering, process control, and basically process simulation is a tool that helps you to get through your daily tasks. Imagine you will do a mass balance for an entire refinery or a petrochemical plant. It will take you days to do a case study to change a certain parameter from X1 to X2, and then see how is the entire mass balance of the plant is changing. So a simulation is nothing but a tool that helps you as a future aspiring, inshallah, process engineer in your career to conduct the study and get the results that you require, and interpret those results to satisfy your job needs. طبعا, as I said, it's a tool. So whatever numbers that you are putting in, based on the quality of your input, you will get your output. So it can be good results, or it can be garbage in, garbage out. So it will not solve your issues. As an engineer, you are responsible for your results. You are responsible to validate your results. But nonetheless, it will save your time and save your energy and let you focus more on your engineering sense rather than the time and calculation. طبعا we will be going through Aspen HYSYS, but basically Aspen HYSYS is one software of an entire suite by Aspen Tech. There is another software which is Aspen Plus, which is also equally يعني familiar in the industry. We mainly use those softwares to conduct our process studies, such as if I want to optimize a process, I want to reduce energy use across my plant, I want to predict a certain behavior. What if I change the feed quality? What will happen to my distillation? What will be the reboiler duty? How can I reduce the reboiler energy cost? How can I increase my product purity if I have an issue in the quality of my product? And many other things. HYSYS mainly would be used if you are working in the upstream or in the oil and gas and refining, and Aspen Plus is if you are working mainly in the chemicals or specialty chemicals industry, such as the polymer industry, etc. But for our purpose, we will go through Aspen HYSYS. And as far as I remember, that you have version 11, so I believe we will not have that significant, we will not have difference in the user interface. And even if you have a different version, there most likely will not be that significant difference. This is basically, once you run the HYSYS, this is the first page that will come up to you. Normally, when you want to perform a new simulation, you click on a new, and in the process simulation, you have two major tasks. One task is to define your what we call properties, which is nothing but to define your components. What are the components that you are going to use? What is your system composed of? Is it water, hydrocarbons? And basically, once you get your system, you want to perform mass and energy balance, and you want to do unit operation calculation. So that will depend mainly on the fluid properties, and the fluid properties will be calculated using equations of state, such as ideal gas equation of state or Peng-Robinson equation of state. So once you start a new simulation in Aspen HYSYS, it will direct you through the properties environment. In the properties environment, you will need to identify what are the components that you will use in your system. For example, when I click on add, it will give you a huge database of components, from hydrocarbons to petrochemical products, and many. So the way you search for a component is basically you can scroll, or you can type in the components that you're looking for, such as hexane, water, and then once you find your component, you can double click or you can click add and it will appear on your selected window. So once you select your component, you will need to select a fluid package. What is a fluid package? A fluid package is nothing but a set of thermodynamic equations of state. And if someone can remind me, what do we use? Yani why do we use a thermodynamic equations?
Yes.
Yes, go ahead, please.
To correct the non-ideality of the solution or the gas.
Correct, yes. But I want يعني more basic, like why, let's assume that I'm gonna use an ideal equation of state. So why do I need it?
To minimize the error, the percentage error, because fluid package give you more precise values.
But what will be the outcome from the package? What will it?
To get the other properties, like if I have the pressure, I get the other properties. If I have one constant property of a gas, I got other property by the equation of state.
Correct. So basically, to calculate the properties of the components or the mixture of components in your system, such as enthalpy, Gibbs free energy, etc. So once you click on add here in the properties, it will give you a list of names. Some names might be familiar, others might not be so familiar, like Antoine equation. We might, if you studied 303, you might be familiar with Pink Robinson, NRTL, SRK, and all the others are just extensions or other equations of state that are developed for specific use or specific process or system. Now, if from your thermodynamic course, if you can tell me, I have a big list here of thermodynamic equations. So which one should I go with? What would be the basis of my selection? How can I select the right thermodynamic property?
It depends on the component itself.
Yes. How? I'm not sure if someone is raising hand or something, but I would prefer if we can just open the mic and let us chat together while I'm viewing the screen. It will be hard for me to read the chat.
I think it depends on the pressure and the state of the component itself. For example, if it is liquid, you cannot use varial equation of state. And if the pressure is high, it's preferred to use van der Waals equation.
Excellent. So pressure can play a role. Why pressure is important? I mean, what does it mean that, let's say, if the pressure is high? If you recall from the ideal gas equation of state, what is the basis or the assumptions that we have? Is that the pressure is what?
Proportional to the temperature. When you increase the pressure, the temperature will be lower.
But is it the ideal gas equation of state, let's say, is it applicable at high pressure or low pressure?
Low pressure, almost 1 bar or 1 atmosphere.
Correct. So that means once we start increasing the pressure, we will be deviating from the ideal equation of state, and this is where the cubic, for example, equation of state, like Ping-Robinson, SRK, what they are doing, they are adding corrections or they are adding parameters to correct the equations to account for those non-idealities at elevated pressures. So basically, the selection of the thermodynamic package will depend on your, let's say, process conditions, such as temperature, pressure, and more specifically pressure. It will also depend on the kind of components that you are selecting. Are you selecting hydrocarbons? Are you selecting water? Is it single component or multiple components? If it is multiple component, are they forming ideal mixture, or they will not form ideal mixture? In this case, you might use, for example, activity coefficient rather than cubic equation of state, and etc., etc. And it can be actually overwhelming to just go directly and select the right thermodynamic equation. So luckily we have let's say an assistant here. If you go to the menu at the top, we have what is called a method assistant. So this will guide you to select the most appropriate equation of state based on your application. So once you click on it, you will have this page popping up, and it will tell you what is the kind of process that you are selecting. Is it oil and gas, refining, chemical? So if we, for example, select refining, it will give you a set of equations that you can use. Ping-Robinson, Grayson, or SRK even. If we select chemical, it will tell you if your pressure is low, then activity coefficient is appropriate, such as an RTL, Van Laar. However, at higher pressure, then you would need to use cubic equations of state, and you have those pre-selections. So you can take a look at that, and from those lists, it will guide you to the most appropriate fluid package. Other option is that you can actually go through the literature and explore yourself. For example, if you see a literature that is utilizing process simulation or calculating thermodynamic properties for a certain set of system, then you can see and correlate what is the most suitable equation of state to use. Else you can go to the help document, which is very useful. So normally this is, let's say, the most basic function of the first environment, which we talked about, properties. This is where you set up your components and the basis to calculate your thermodynamic properties of a system. It is very simple. Sometimes you can actually have a mixture of components, such as, let's say, methane, ethane, butane, etc., like mixture of hydrocarbons. And when you have a mixture, you have interactions between the two components. So in some cases, when you select the equation of state, you will need to define what is called the binary coefficient. This is basically nothing but a parameter that describes the attractive or repulsive forces between the two the binary mixtures. Whether they like each other, they will stick to each other, or they will repel from each other. You have taken the 306 and you know the McCabe-Thiele diagram. So you might be able to distinguish the difference between an ideal mixture and a non-ideal mixture. So if someone can tell me, for example, if we have like a mixture of water and ethanol, like water and alcohol, this will form an unideal mixture, and sometimes you will reach up to a point where the composition in the vapor and liquid phase will be the same. So you will not be able to make the component any more pure than that. So can someone tell me what is this kind of behavior, or what is the property related to this kind of behavior?
Is it isotopes?
Yes, exactly. So when you have an azeotrope, you will have a certain point in the vapor-liquid equilibrium where basically you cannot pass. So you will reach that point and you will not be able to further separate. And in the industry, you will face a lot of systems that have azeotropic mixtures, and you will be forced to either change the pressure or use a third component that use a different technique than conventional distillation to be able to separate the two mixtures. So sometimes you will need to set up those binary coefficients. However, for most of the cases, especially when you have ideal mixture, like hydrocarbons, and especially when you are using a cubic equation of state, most of the time you will not need to define those binary coefficients, because they will be pop up by default, because Aspen is storing those and it has a huge database in it. But in case it was needed, you can easily look it up in the open literatures. They are widely available for most of the systems. So while I'm explaining, I would actually like to pull up the assignments, and from there we can just have a look and try to apply the thing. Of course, I will try not to solve it, but we will try to see what are the kind of features that you will use in Aspen HYSYS to help you solve this problem and inshallah future problems that you have in the in your career or your academic life. So the problem statement is to design a distillation column that will separate a feed of a 50-50% water and methanol at 25 degrees Celsius and 1.4 bar, with methanol recovery of 95% in the distillate and recovery of 99% in the bottom. So we are assuming total condenser operating at 1 bar, and we are using SRK as the property method. So we know we have a system that is consisting of water and methanol. So if I run a new case, open a new case, so again it will take me to the property environment. So from the first thing is that I need to define my component. So I just simply go click add, and from here I just simply type in the components that I'm looking for, such as water and methanol. You can, by the way, search by the name, or you can search by the chemical formula. So you will have different options. Let's say, for example, for the formula, if I want to select ethylenes, which is C2H4, so I will search by the formula and it will give it to me. So I've selected my component, and I see the blue mark is ticked. That means I fully defined the component list. The next thing, which is shown in red, is the fluid package, which is the thermodynamic equations that we are supposed to select. And as per the problem statement, that we are supposed to use SRK as the property method. So I basically, again, when I click add on the fluid package, I will scroll down and look until I find the SRK. So once I select it, you see it gives me OK green. That means there is nothing else that I need to input in the property package. And by that, I finished setting up my property environment, and now I can move to the simulation environment to start building my flow sheet. So once you open up your simulation environment, you will have your flow sheet, and then you will have your top ribbon, and then you will have your what is called the model palette, which includes all the unit operation that you will be using, or logical operation that you will be using to build up your flow sheet. Just quickly, I want to give you an overview of the several different functions that we can use and the simulation. So starting with the home tab, basically this is where you define your unit of measurement. So if you are interested to customize your units, like for let's say you want your pressure, for example, or your energy, and rather than a calorie, you want it, for example, in kilowatt or megawatt. You can change that, and you can do the same for mass flow rate, pressure, temperature, etc. So you can select your preferred set, or you can basically select one of them. There's like SI unit or English unit, etc. And you can also customize the display of your numbers. Like for example, how many decimal points, how many significant figures you need for each of the variables. You can also define your standard temperature and ambient pressure in here. Most of the cases you don't use those, but in case you want to define your standard volume flow rate, then in that case you will need to play with those parameters. So once you are happy, you can click OK, and you can have your unit of measurement set. Next, you will have your utility managers, adjust and fluid packages in case you have multiple thermodynamic equations. By the way, you can use multiple thermodynamic equations in the same simulation, but that will be an advanced level that we can inshallah cover in upcoming workshops. You have also your utility manager in case you are using utilities such as electricity, steam, cooling water, and you want to calculate the cost of your utilities. This is important, which is your solver. It should be on active, because if it is on hold, your flow sheet will not solve. So sometimes if you put your input and you are trying to just get the model solved, but it's not solving, nothing is happening, most likely your solver is on hold, so make sure you activate it. You also have your reports in case you want to build up a report for your results. You have an analysis feature where you can do sizing of your equipment. You can do stream analysis, such as vapor liquid equilibrium, for example. You can do case studies, optimize surge analysis for your compressor. You can do safety analysis such as calculation of emissions or sizing of a pressure relief valve or flare system. You also have economic analysis, and this will be helpful for you when you are in your senior design year project that you can use this feature to help you in the simulation when you are doing your process economics, and it will also help you in your career to quickly build up your business case. Most of the cases we are dealing with the steady state, and even when you go to the plant, majority of the cases that you will be dealing with is a steady state. Can someone tell me what a steady state means? What does it mean when they say the process is in a steady state?
Does not change with time.
Yes. So the variable is constant with time, although in reality you will not see a variable like a temperature that is constant over time, but on average the fluctuation is considered like a steady state. So that's why most of the time in real life we simplify the process to be a steady state. Otherwise, it will always be complicated to solve an issue or to model a process in the real time. However, if you absolutely need to model a dynamic behavior, let's say I have a change in my flow rate. how is that gonna affect my inventory? How is that gonna affect my heat transfer over time? How long will it take to fill a certain tank? How long will it take to heat or cool down, like during startup or shutdown conditions of the plant? You can do the simulations here using dynamic. You can also connect your simulation to plant data, but this is not applicable in our case. Equation oriented, this is just a way to solve your equations or your process simulation. Again, this will not be applicable as I would say 99 or 90% of the problems that we encounter, we don't need to use this feature. It is for extremely complex systems where we need the whole simulation to solve all at once at the same time. However, the current way that the simulation will solve block by block, for example, if we have a heat exchanger, then a separator, then a reactor, so it will solve it like a heat exchanger, then the result will be sent to the flash vessel, then to the reactor, etc. And in most of the cases, that is more than enough. And mainly, this is what you need. You can go to the flow sheet here to display a certain variable like temperature, pressure, or sometimes flow rate, and in the streams. Next here, basically in this model palette, whatever components that you need to simulate, from heat exchangers to reactors to distillation columns, you can find them in handy in here, and you can basically filter them out. So if you are only looking about heat transfer equipment, that is heat exchanger, fired heater, air cooler, or let's say you want to model a reactor, so you are only interested to show the reactor sections, so you will see your CSTRs, your plug flow reactors, etc. Or if you are looking for separators, be it flash vessel, flash drum, be it distillation, extraction column, etc. And you also have something like logical operators. Like when you want to input a certain formula, for example, I want to set a certain temperature for a certain stream, or I want to correlate one stream to the other, then I would use those manipulators. So this is mainly your simulation flow sheet. You will need to build your flow sheet in here. So let us start from the assignment. Let us see what it says in here, that design a distillation column that will separate a feed. Okay, so we have a flow rate, and we have a composition, we have temperature, and we have a pressure. So how we can define that? We have streams in here. So you have material stream and you have energy stream. Material stream will hold components, or your components that you are defining. An energy stream is when you define an energy flow. For example, when you have a pump, you need a power or energy to run that pump. So in that case, you will supply energy to the pump. Or when you have an expander, then or a turbine, then you will get energy out of that turbine as you are reducing the pressure. So that's when you are using energy stream. But in our case, we will use a material stream. So you can drag and drop, or you can click and then click on the flow sheet to have your material stream. Then once you double click, you will you will have many empty fields in here, and you don't actually need to fill all of them. For the state variables, like for example temperature, pressure, and vapor fractions, you will only need to fill 2, and the third one will be calculated. And you will need to define your mass flow and your composition. So because when you have your thermodynamic equation and you know your composition and your temperature and pressure and you know the mass flow, I can calculate the volumetric flow rate. I can calculate the molar flow rate from the molecular weight. I can, because I know the state, like the temperature and pressure, I can calculate the enthalpies. Or if I define the molar flow rate, I can calculate the mass flow rate, etc. If I say this is a saturated liquid or vapor and I specify a pressure, then automatically the temperature will be calculated from equilibrium. So the message here is that you don't need to define all of those. You only need to define 3 variables, mainly 2 state variable like temperature, pressure, or vapor fraction, and any of those. And you need to define your mass flow rate, or molar flow rate, or volume flow rate, one of the flows in here. The rest will be calculated if you define your compositions. Okay, so in our case, we are given the temperature, which is 25. We are given the pressure, which is 1.4 bar. By the way, as you can see here, that the units are set to Celsius, bar, kilogram per hour. If that is not the case in your case, you can change the units from the unit set that you have in here, or you can build your own. Next, we are given the molar flow rate, which is 100 kilomole per hour. So in this case, I will input the molar flow rate. You see here it says kilogram mole, which is the same as kilomole in our case. And then it is a 50-50 mixture. So once you go here, normally what I do, I don't write the numbers directly. I would go to edit, and then I would specify whether I need to define it on mole basis or mass basis, or in terms of flows rather than fractions. In our case, it is 50-50 mole percent, so I'd keep it at mole fractions, which is 0.5. So once I click OK, you see the stream turns into, or the status turns into OK. And if we go back, we see the rest of the variables are defined, and you can also see the properties here populated, like density, molecular weight, heat capacities, etc., which are calculated using our thermodynamic equations of states. So we have defined our stream. So let us explore some of the tasks, and let us explore some of the features that we have in the process simulation to help us conduct those tasks. So here the first thing is to plot the XY equilibrium curve using HYSYS. So can someone tell me what is the XY equilibrium curve? What does it give us? What is the use of it?
we can determine if we have isotopes in the mixture itself when separating the components.
Exactly. So we can look at the nature of the mixture, how it is behaving. Is it ideal, non-ideal? I can use it to do the manual calculation if I select, like to do the McCabe-Thiele method to determine the number of stages. I can do many things with it. So how do I plot the XY equilibrium curve? Basically, okay, so if I on the model palette itself, there is a unit operation which is called equilibrium, which is and those sorry, those opposing arrows that are shown in here. So you can just simply click on them, and once you double click, so this will be, this is where you determine your equilibrium plots. So if you have a binary mixture, which is a mixture of two components, or ternary mixtures, which is a mixture of three components. In our case, we only have water and methanol, so it is a binary mixture. What we need to do is that we need to actually go here on those components and select them or add them, because sometimes you will have, let's say, 10 or more components. So what is the binary mixture that you need to have? You should select it. You should like click on it and select add, so that you activate it, let's say, in this unit operation. Then what you need to do is that what is it that you are plotting? Are you plotting XY plot, which is vapor versus liquid curve, which is like, for example, liquid on the x-axis and then vapor on the y-axis, or you are looking for TXY, which is basically you will have on the x-axis temperature, or PXY, where you will have on the x-axis pressure. So in our case, we are tasked to plot the XY equilibrium curve, which is the selected plot in this case. What you will need to do is that you need to define your pressure or temperature or both, so that you can generate your plot. You need to determine what is your equilibrium conditions, which is your pressure and temperature. In our case, we have 1.4 bar, and basically once you input one, the other will be calculated. So you see, once we input pressure, this is no more active, because we have satisfied our degree of freedom now, and the status here will be updated, and it will say update plot. So just click on the plot, and it will plot for you the XY diagram. So this is your XY curve, and here on the x-axis you have mole fraction of water, and here you have mole fraction of water vapor on the y-axis. So I keep talking a lot, but gentlemen, let me know if what I'm explaining is clear, or do you have any doubts or questions?
Mr. Muhammad,
Yes.
shouldn't the pressure be 1 bar?
You can select whatever pressure you want. It depends on the conditions that you want. Okay, so we are doing the equilibrium at 1.4 bar, but yes, if we, let's say, want to do the distillation at 1 bar, then you are absolutely right. We need to do it at 1 bar, and then we can update the plot, and then we can generate it once again. So yeah, so this is a good point. You should do the equilibrium at the pressure or the conditions of your equipment, not your feed, or you should know the conditions at which you are separating your components. But yeah, this is a good point. Thank you very much. So I'm hoping that this is clear for everyone. If anyone has any question. Okay, so I'll take that this is clear. Please feel free to interrupt if you have any question while we are explaining. Okay, so now we are getting into the heavy stuff. So what is actually our task is to design a distillation column to achieve our objective of 99% recovery of water at the bottom and 95% recovery of methanol at the top. So in 306, and normally when you do hand calculation, how would you design a distillation column? What is the tool that you would normally use? Or okay, let me put the question like this. When I tell you to design a distillation column, not to do sizing, but let's say a distillation in terms of the number of stages, what would be your approach? What kind of tools that you would use to determine the number of stages?
McCabe.
Equilibrium curve and
McCabe and CMO.
Yeah, and how would you use that method? So mainly, for example, you will be given the feed conditions, and you might be given the operating line equation, or you will be given the product, and like, for example, the reflux. So you will need to plot your operating line, and then you should know your the outlet conditions, or based on your problem statement. Then you will need to determine your number of stages from there, and this will tell you based on your operating condition, like your reflux, etc., what would be the number of equilibrium stages required to achieve your separation. But have you studied any other methods other than the McCabe-Thiele diagram?
Stage by stage.
Okay. Yes, you can. There are many other methods. McCabe field is will give you, for example, the number of stages. You can also have other shortcut methods, like if I spell it correctly, Underwood Gilliland method or something. If you have studied that as well in your 306, that can also estimate the number of stages for you. So what we are going to do here is that we are not going to use the McCabe field diagram, but we are going to use other methods that will help us design our distillation column. Now, if I simply go and select, for example, a distillation column, let me see. So this is, by the way, your distillation column. If I select the distillation column and try to define it, it will ask me to input the number of stages, and then it will ask me to define other parameters, like when I try to get it configured. At this stage, I don't know even what is the number of stages to input into this configuration window. So this will not really help me. So one way is that I can do offline the McCabe field and then determine the number of stages from there and the feed stage, etc. Else, I can use what is called a shortcut distillation. So in the shortcut distillation, I can actually supply a few inputs in there, and it can calculate for me the majority of the variables that I would need to configure my rigorous distillation model. So I would use the shortcut not as a final model, but I would only use it as a start guide to determine the number of stages, the feed stage, etc., like for initial results. And then I will take those results and then I will convert it into a rigorous distillation column. So once we have the shortcut column, we basically what we need to identify or define is to define the connection into and out of the column. So our inlet would be our feed, which is the feed stream which we have just defined. And then I need to define an energy stream for the condenser duty. I can just write in any name like QC, which is for condenser. And then distillate, and say anything like top. And then reboiler duty, for example, QB. And then bottoms. And click on bottoms. So now it's important here to say whether our top product phase is liquid or vapor. So how do I know if my product is liquid or vapor from, let's say, this problem statement?
It says a total condenser, so it's liquid.
Okay, excellent. Very good. So yeah, so if we have a total condenser, we will have a liquid. What other kind of condensers that we might have?
Partial condenser.
Partial condenser, and what would be the products out of that condenser?
A mixture, gas and liquid.
Yes. So it's not only vapor. Excellent. You don't need simulation. خلاص, you can solve by your own. Very good. So now I define the connections. I see in the status bar, it will give you hints sometimes what is the next step you need to do. Once we define the connections, we can go to the parameters tab. And the parameters, I define, I think this is also something that we have come across, which is the light key and the heavy key components. What does a light key component mean, or heavy key?
More volatile and less volatile.
Let's say I have a mixture of 4 components. Let's say ethane, propane, butane, and pentane, for example. Does it always light key will always be ethane?
No.
Why?
Light key component, it will be the component that we want it in the distilled.
Yes, exactly. Which is our main product, right?
Yes.
And also for the bottom, which is the heavy key, it will be the same thing. So when we say what is the light key, this really depends on our our system, our requirements. So so we need to define our light key, and just don't please try to pay attention here that it says light key in the bottoms. That means how much of the light key in the bottoms of the column. Here we have simple system. So definitely one will be light key and one will be heavy key. So if someone can guide me, which component is the heavy and which component is the light key?
The heavy is the water.
Yes, heavy component is the water. So light key component in the bottom would be the methanol, and then the heavy key is the water. Okay. Now, what we are given in the problem statement, we are given a flow rate, which is 100 kilomole per hour, and we are given a composition of the feed, and then we are given a recovery. However, a simulation here is asking us for mole fraction. Mole fraction of the light key in the bottom and mole fraction of the heavy key in the distillate. So we don't have that in the problem statement. How can we get it?
He said in the question fraction recovery is 95 for the distillate. That means D times XD, it is 0.95 times 0.5 times 100. And the same for the bottom.
So you mean we will calculate the component mole flow rate, all right? Is that what you're saying? Let us set up an Excel calculator here very quickly. Okay, so we have our F, is our feed, and then H2O recovery, and then methanol recovery. So here we have 100 kilomole per hour, and this is 95. So this is 0.99 recovery in the bottoms, and this is 0.95 recovery in the top. So how to get XD, which is or let's say, how do we get X methanol in the bottoms from the given information? Of course, we have here the composition, feed H2O, and then feed and 0.5. So can someone help me how to do the calculation?
We need to find the distillate and the bottoms first.
Okay. You mean the distillate what, mole fractions or flow rates or?
Flow rate. So we can get the mole fraction.
Okay, how do we do that?
We can say 100 times 0.5 times 0.99 or 0.95. And then we add it to the bottoms. So we get the distillate.
Okay, so what should I do? Here, if you just guide me through the calculation. So the feed.
Times mole fraction.
Yes.
Times 0.95 for
Yes. So this is what?
the flow rate of the methanol and the distillate.
Right. So this is D. Kilomole per hour. Okay.
Same thing for the water.
And then for water would be again 100
times
multiplied
0.5.
by what? Multiply by
0.01. No, 0.01.
Yes, excellent. And the summation, this would be your distillate flow rate. Then basically it is يعني 201. You divide the flow rate of the component by the total flow rate. This would be your mole fraction
XD.
Yes, this would be your XT. However, what we are looking for is actually not this one. What we are looking for is, or what the simulation is asking is water composition in the distillate, which would be 1 minus XD, which is this value. So we need to do this for water, and then we need to do the same for the methanol. So what would be
0.5 divided by 48.
0.5
divided by 48.
divided by 48?
Yes.
Okay, this is what?
The heavy key in the distillate.
Yes, exactly, or exactly. So which is this value? So it can be either 1 minus the XD, well, which is for methanol, or 0.5 directly, yes, divided by 48. Now, what about the light key in the bottom? How do we find that?
One minus
what?
For the heavy key in the distillate, you mean?
The heavy, no, the light key in the bottom. We already find the heavy key in the distillate. We plot it here, or we plugged it into HYSYS. But what about the light key in the bottom?
We know that the bottom flow rate is 52 because from mass balance 100 minus 48, the total flow rate of the bottom is 52.
Okay.
So 100 times 0.5 divided by 52.
100
times
0.5.
Yes. Divided by 52.
Divided by 52. And what is this? Sorry, divided by 52. What is this?
It's the heavy key in the bottoms.
I think I think we should multiply it by 0.99, the recovery.
Okay. So actually we'll do the same. Okay, I'll leave this number here. So we should exactly let us do the same practice, and this will be your 49, and then what would be your methanol? Multiply this, and then multiply by 0.05, correct? So then your your water would be 49.5 divided by 52, which is 95%. And then your methanol is actually 2.5, which is this value, correct? Yes, gentlemen?
Yes, correct.
So we have defined the mole fraction. I know it's simulation, and we still had to do some hand calculation, but sometimes there is no escapement. So then the pressures from the problem statement. We have the condenser pressure, which is operating at 1 bar. The reboiler pressure, I don't see anything here mentioning about the reboiler pressure. So what we will do, we will just assume 0 pressure drop across the column. So that means the reboiler pressure is the same as the condenser pressure. So if you can see that the simulation will calculate for us the minimum reflux ratio, and this is good because now for number 2, it says find the optimal design using shortcut method, tool of Aspen-Heises, which is what we did, assuming a reflux ratio equal to 1.6 times R minimum. So that means what we should put here in the external reflux, 1.6 times 0.654. So this would be our external reflux. So once we do that, heavy calculations. Sorry if someone said something. Okay. Once we do that, we solve our model. So what do we need to do now? What is the goal really of doing all of this? We need to have our stages needed for separation, feed stage, etc. The reboiler duty. So if we go to the performance tab, we can see the calculated results. For example, what is the minimum number of stages, and what is the actual number of stages or trays, and what is the optimum feed stage? What are the condenser temperatures and reboiler temperatures? What are the duties for the condenser and reboiler? So we have those numbers in front of us. So if as you can see that the shortcut column gave us a majority of the data that we needed to build our distillation column based only on the product fractions, pressures, and the external reflux as a function of the minimum reflux ratio. So it is only requiring minimum input. And so you get your results for the shortcut here, which is the number of stages, and then you can also get your product stream properties from this worksheet, as well as the compositions. So now you are able to obtain your number of stages, or let's say your distillation column design. So so far, anyone has any question on whatever that we have done? Or yani, inshallah, you will feel confident that you know how to use a shortcut distillation column.
Explained properly.
Sorry?
I said it is explained properly. Thank you.
طيب الله يعطيكم العافية. So the goal is only basically to get those basic data, which is any number of stages and the feed stage. So just now, sometimes when you close this model palette by accident, you can simply go to the view and you can click on model palette, or you can click F4 and it will pop up again. So using the results from the shortcut method, design and simulate the distillation column. So basically what you will do next, as we said, if you go to the separator, this is not your distillation column design. This is just a way to get the data that you will need to design your distillation column. So you go again to separators, you hover by the mouse over it, and you will see that this is the distillation column. There are other columns as well, but this is what we will need. So the page is a little bit more complex, but still we still need to define our feed stream. We still need to define our stages, etc. Now the feed is already connected to the shortcut. So what I will do, I can just type in feed, for example. It will generate a new stream for me. I will show you later on how we can define it. Then again, I will simply redefine the streams. So we said here that the condenser is total condenser. So it will remove the vapor product. So this is the overhead. I'm just changing the names here because HYSYS doesn't allow me to replicate the names over and over. And Q boiler. And then here, this is bottoms. Okay, I already defined bottoms. So okay, what was the number of stages? It was 11, I think, 11.2. So what is the number that I should put in here?
We should round it up.
12.
Exactly. You should always
I think 10.
10?
لا 12.
Always, if you have a fraction of a tray, even if it is 0.1 or 0.9, you should always round it up. So in this case, we have 11 point. If we have 11 point something, so we should always round it up. And then similarly for the feed stage, it was 7 point something, 7.5. So we'll put 8. And then once you define those parameters, you can simply click on next. This is to select the configuration of the reboiler. In most of the cases, you don't really need to change anything. You just leave it as default. If you are simulating an existing column, for example, for the industry, and you know the configuration of the reboiler as circulation with the baffle, for example, then you can continue. You can configure it as that. But for now, the default is more than sufficient for us, and it is simple to solve as well. So here we will define the condenser pressure, which is 1, and the reboiler pressure. In real life, you normally have the reboiler higher than condenser, but it is a fair assumption to assume no pressure drop across the column so far. If you have complex system, complicated distillation, sometimes you need to provide estimates. It will help in finding the solution quicker. But we have a simple system, so we really don't need to bother ourselves of putting a temperature estimate. But if we need to, we already saw that we have condenser and reboiler temperature, so we can supply it if we need so. So here we can define the reflux ratio or the liquid rate. We have just defined the reflux ratio here, which is 1. This value. So I will just input the value in here, and then خلاص, I will select done.
Excuse me.
Yes.
الليكويد ريت مو المفروض نحطه نفس اللي طلعنا الديستلت اللي هو 48 كيلو مول بير اور.
You can. احنا طبعا الحين حطينا كل الانبوتس we click done. We can always go back and change, add even more specification than the liquid rate, or put nothing at all at the beginning. We will see now. We will see how we can specify the column. So I will open. I hope it will allow me. I will open both. Good. Okay, very good. So on the left hand side, this is the short column result. So yes, I think we did the number of trays correctly. Very good. So once you build your distillation column, you need to solve it. But before you solve it, you should go to the monitor. And by the way, this is maybe the most complicated system or unit operation most of the time in process simulation, and it is most of the time painful to solve. So what do we have in here? What we can see in this monitor for the distillation column, we can see what are the specifications that we are specifying and what is our degree of freedom. So we have 2 active specifications, and these specifications indicating our degree of freedom is 0. That means we need 2 specifications for us to solve the system. So let me just deactivate those. You see the degree of freedom will update to 2. That means we require 2 information so that we can solve our system. So I have the reflux ratio. Okay, good. That means I'm still left with 1 degree of freedom. Now here I am free. I can specify the distillate rate. I can specify the composition of the distillate. I can specify the recovery. I can add a specification here, and you can see I have many options. I can specify the duty, I can specify the recovery, I can specify temperatures, for example, across the column. So many options I have in here. So I can, for example, select column component recovery, and because we have this information in our problem statement, so I can rename this to methanol, and in the overhead, basically, I have 95% recovery of methanol, and I will just close that, and then I will deactivate the reflux ratio. I will add another specification for water, and here, which is H2O, and this will be in the bottoms on molar basis as well, is 99% of water recovery. So this will be the recovery, fractional recovery of water, and then I will also click on exit. Now what I need to do, okay, I have the degree of freedom, I have the two specifications defined. I need to hit run. Okay, why it did not solve? Because remember, we have defined the feed, and the feed is empty here. We need to input the information. I can either do the entry of the information manually, as I did for the first stream, or I can do a quick trick and I can copy the information from this stream to my feed. So in this case, what I can do is that select on define from stream and select my stream, which is number 1, and then click OK. So it will take all the data from that stream to my new stream, and you will see all the information is copied exactly. And I can change it if I need to. Now, once I define that, you see my column has solved. Very good. So let us just quickly explore the results. Now, let us see just comparing the condenser duty or the reboiler duty, whichever. Now here, for example, the condenser duty is 1,531 kilowatt, while here it is 1,041.4 kilowatt. Similarly, for the reboiler duty, this is 1,600, and here it is around 1,200. So why do you think there is a difference? Did we do something wrong?
Maybe because it's in the first one, it depends on the reflex ratio, and the second one on the the recovery, fractional recovery.
Okay, but well, aren't we supposed to? Because okay, yes, this depends on the recovery, but also here in a way we input the recovery. I mean, we input the mole fractions that will basically be translated to the recovery. In fact, let me even show you something. If I go back to design and monitor, so our reflux, what we said here will be 1.6, right? But you see the calculated reflux is actually 2, so it's double the almost double the reflux that we anticipated will be at the beginning. So why we are having such difference? Again, it is different equations, different models. A shortcut is a shortcut. It is a very rough estimation, quick estimation for the number of trays, the feed location, etc. While the rigorous distillation, it does tray by tray calculation, and it gives you more accurate results than the shortcut column. So if you are to use any of the two, you should use the rigorous distillation column and not the shortcut, because this will give you more likely reliable results. So if I want to estimate the duty, I will not look at the duties here in the shortcut. I would rather be more confident with those values than the shortcut column, because shortcut is a shortcut from the name itself. So the calculation is different, formulas are different, and the purpose is different. Here I'm trying to simulate an actual distillation column, whereas here I'm trying to get initial estimates to build my actual simulation column. I hope this is clear.
Excuse me.
Yes.
What is the specification you put when you add the specification for the fractional recovery? What is the name of the specification?
Okay, so you can add a spec. Once you click on add spec, you will have this menu. So what I selected is column component recovery, and this is just one way to specify the column. You can specify other parameters. I can specify the reflux ratio, for example. Let me disable one of the component recoveries, and I will specify the reflux ratio. So when I solve, you see it will solve, but now it will give me a fractional recovery for water that is different than 99%, because I need higher reflux ratio in order to satisfy the fractional recovery. So I would always prefer to specify mole fractions or my target recoveries and have the other variables calculated. Otherwise, I can specify the flow of the distillate or the flow of the bottom product, but I need to make sure that my calculated or predicted mole fractions and I need to check all the other calculated parameters and ensure whether they are realistic, reasonable or not. So what we see, for example, distillate rate is 47.99, which is almost 48. Correct, it is matching our calculation, and then 52 for the bottom products, which is again very good.
قبل شوية لما سويت رن قلت إنه في مشكلة في الفيد.
Yes.
إيش هي؟ إيش المشكلة؟
اوكي رايت. احنا لما سوينا configuration حق الديستليشن كولوم الفيد كان empty، ما كان في اي داتا. يعني لما اعرف انا ديستليشن كولوم جديد ما حطيت اي فيد ماتيريال، فلما احط له فيد هنا راح ينضاف لي فيد ستريم، لكن راح يكون فاضي، فراح احتاج اعرفه ولا ما راح يحل الديستليشن كولوم. It will not solve. What I did is that I defined basically the feed stream so that I was able to solve my distillation column model. Clear?
Yes, yes.
Excuse me, I have a question. You said for the shortcut method, we cannot rely on the results of the heat duties. But why we can rely on the number of trails?
Okay. It will give you number of trays and it will give you feed trays. The optimum feed location, right? So even when you go, let's say you are working in a distillation column design company, even when you get those number of stages and the feed stage, and you directly, let's say, try to design an actual distillation column with those figures, most likely you will not get the correct design. In fact, almost always you will not get the correct design. This is initial to help you set up your distillation, but then there will be many factors that will play. يعني and let me ask you a question. Now when I select, احنا الحين we selected stage 8 as a feed stage. I can maybe most of the time alter the feed stage by 1 or 2 stages and it will still solve. I can select 7, maybe it will solve. Yes, I can maybe even select 6. I think it should solve. But okay, it will solve. But if you go back and see now the duties, they are increasing very much, more than 8. So when you get the values from the shortcut, it will most likely give you the optimum feed location. That means the feed location that will give you the minimum condenser and reboiler duties. But when you go back to the rigorous distillation, you might have the factor of tray efficiency. So this is 12 stages. Here we are assuming 100% efficiency of the trays, which is never the case in real life. You might have efficiencies down to maybe 60%, and the efficiency will not be the same for every stage. So that means this will be only a starting point. Then you will need to study your system, and then depending on the type of trays that you are configuring, which is something else you can do in HYSYS, it will give you more realistic performance for your distillation column. By that, you might need to increase the number of stages a little bit to achieve the separation, or you might need to change your feed location to optimize the energy both on the reboiler and condenser. So even I would say the number of stages, the feed location, for our purpose here we can rely on it, but when you go to the real life, you will still need to do huge exercise in selecting the number of stages and the actual feed location.
Okay, thank you.
عندي سؤال بس، السبيسيفيكيشن حقت الفيد حقت الكولوم هي نفسها حقت الشورت كت؟
Yes. Now we can, as I said earlier, I can type in the specification directly as I did. بس الexercise اللي I did هنا انه which we can replicate quickly again. لما يكون عندي stream that I يعني ابغى اسوي define حق الستريم هذا to be the same as الفيد للشورتكت. I can double click, I can go to define from stream, select the stream which is going to the shortcut, click on it and then click OK. It will copy all the data in here. So this is basically what I did for the rigorous distillation.
Okay, clear.
Okay, so I'm not gonna attempt to solve all of the homework, but I will try to show you the tools that you would need. For example, let us quickly go through the questions using the results from the shortcut, design, and simulate the distillation column. We actually achieved, we actually did that. But study the effect of changing the fractional recovery of methanol and the distillate from 90 to 99% on the reboiler duty. So using case studies tool. So this is what we saw earlier. We have a tool here that is called case studies. And what this will do, basically, you are trying to study an effect of one variable on your model. So you will change one variable and you will see how the results will change. You can do that manually. I can go manually and go to monitor, and I can change the recovery step by step, and I can plot the data for the reboiler duty, for example. In this case, it might be simple. It might not take much time, but for more complex system, it might take a long time. So what I can do is that I can have an efficient way, which is case studies. So if I click on case study, okay, I will click add. So here I need to define my independent variables and dependent variables. My independent variable in this case would be the fractional recovery of methanol. So what I can do, I can define the variable from here, from variable manager, or I can find the variable. So I can go and check this is related to for example, the overhead stream, and I can go select for mole, or sorry, recovery. It's okay, main tower. Okay, go to main again. G101, yes. From the tower here, I can. It is somewhere in one of those. It will take you some time to find out the variable. So a quicker and easier way to do is that I can go to the column itself. I can go to monitor, and this is what I want to change, the fractional recovery of methanol. I can right click and then send to case studies, and then case study 1, which is our case study. So once I click that, I close, I go to case study, I will see it populated here. So the same thing I can do for the dependent variable, which is in this case the reboiler duty. I can double click on the distillation column. Those reboiler and these things, you find it normally in the performance tab. We haven't gone through those tabs, I know, but I'm just trying to save the time because I think I took much of your time here. So you do the same thing. You send it to case study 1. So once you do that, you close, and then okay, so this is in the independent variable. It should be sent to dependent variable. Okay, so I will simply go then to tower 101, then I will type in duty, and then I will have reboiler duty, and then done, and then I will have this. So I will go, so I define my dependent and independent variable. I will go next, case study setup. I will select the start and end point. I will just maybe select 94 to 0.96, and then I can either select the number of steps or the step size, so maybe 0.005, and then click on run. So it will run, it will give you the results. So I can see as I change the recovery of methanol, how the reboiler duty is increasing or decreasing. So I can see that in a table. I can copy it to Excel, or I can directly plot it. You can see the plot here. So this is how you would normally use your case study. I can add whatever independent variables I need, and then the dependent variables, and then I can simply set up my case study here and then run it, and I should get the results easily. Yeah, so this is basically the case study function. I hope this is clear for you. If you have any question on the case study. Okay. I would assume it is okay. So here basically it is the same exercise. You would just define the external reflux ratio, and then you would plot in the actual number of trays, but this would be not in your column, this would be in your shortcut. You would do the same thing. You would use the external reflux ratio as an independent variable, and then you would have your actual number of trays and your dependent variables, and then you will change, and then you will observe your results. So I'll leave that up to you to solve it. Hopefully it should be the same, but if there is any difficulties, you can come back to me for any questions. I'll leave my contact details. Now, okay, we are talking here about plotting. So like plotting flows or temperature profiles, how we are going to do that. So normally you go to the distillation columns, you again, you go to the performance tab where it is having most of the results. You can go to plots, or you can go to the plots. Now in the plots, you can plot the temperature profiles. So you can select on temperature and view graph, and it will show you the temperature profile of your column. What is the temperature on each stage? You can plot in the pressure, you can plot in the flow. So it will show you the vapor flow and the liquid flow. And you can infer information from there. What does it indicate to have higher vapor than liquid, or higher liquid than vapor? Or you can plot in the composition to see how the separation is taking place across the column, how the compositions are changing, and if there is any way that you can optimize. And then again, you can go to this, you can view the column profile from here. You can view the condenser and reboiler temperature, pressure, and duties. You can, this is internal result. This is in case you define the mechanical configuration of the column, which is not applicable in this exercise. Yeah, so these are the main results. I think these will cover your most homework. Actually, all of your homework questions in here. I hope this was clear. But please feel free to ask me any question if you need any clarification on any of the things that we explained. This is by no means is meant to be introduction to HYSYS, as we will need much more time to really go through the features. But I just try to focus on whatever that is important and relevant to you in your homework, so that you will get a feeling and understanding of how the simulation software work, and how to deal with distillation columns in a simple manner, to help you get the results or perform the analysis that you need in order to get the results that you're looking for. I hope my explanation was clear for you. So please let me know if you have any questions.
واضح، الله يعطيك العافية.
الله يعافيكم. أنا إن شاء الله ما نومتكم بس يا شباب، أدري حنقرب وقت السحور.
لا لا بالعكس،
ما قصر. يعطيك العافية.
الله يعافيكم. Thank you, gentlemen. It's been a pleasure. Just in case you need any support, I will just leave you my contact details. You can approach me through the email mutawaa.mah@gmail.com. I check my email all the time, so if you need any support or any assistance, please feel free to reach out to me. I will be more than happy to help you with whatever that I know and I can help with. Yeah, I'll just leave it at this. Thank you, gentlemen, for your time. Really appreciate your patience with me. I know I talk a lot, but I hope at least I provided something that will benefit you and will help you, يعني, not only for the homework, but to utilize the software in an efficient manner, inshallah. Thank you, gentlemen. I'll just leave the floor if any clarifications or else الله يعطيكم العافية. دكتور باسم.